Assalamu alaikum. So in this lecture I will try to answer the question, can we judge about the stability without solving the characteristic equation, which means that without finding the exact location of the root of the characteristic equation, can we judge about the stability? And the short answer is yes, using the Joule stability test or the Routh stability coupled with a bilinear transformation. So in this lecture, we'll answer the stability test can be applied directly to the characteristic equation without solving for the roots, which means that without solving the characteristic equation we can judge about the stability, and this can be done using the Joule stability test. And the second one from the continuous control system, which is the Routh stability test. Coupled by bilinear transformation. So in this lecture, I will highlight the using of the Joule stability test to judge about the stability without solving the characteristic equation. So let's discuss the Joule stability test. And to do so, let's assume that we have the following characteristic equation, Q of Z, which can be written as an z to the power n plus an minus 1 zn minus 1, and here we can write a1 z plus a of 0 equal to 0 is my characteristic equation. And here I will assume that an is greater than 0. If not, I will multiply q of z by minus 1 such that a of n is positive. So q of z here, this is my characteristic equation. And you know that if the order of the system is higher than 2 or 3, it will be difficult to find the exact location. So that's why we need to judge about the stability without solving the exact location. So simply, we need to build the Joule table. And after that, I will state the necessary and sufficient condition for the system to be stable. And let's start here with rho. And here let's assume here we have z to the power 0, z to the power 1, z to the power 2, z to the power 3, until here let's assume z to the power n minus k. Here let's assume z n minus 1, and finally here we have z to the power n. Now the first row is taken directly from the characteristic equation, so I will collect the coefficient of z to the power 0. The coefficient of z to the power 0 here is a of 0, so here I will write a of 0. Then I'm searching for the coefficient of z to the power 1, which is here a1, so here would be a1, and so on. So this will be a2, this will be a3, this will be the an minus k, this will be the an minus 1, and finally here this will be the a of n. And that's why I'm selecting the following sequence: an, zn, an minus 1, zn minus 1. Now the second line is actually the first line reversed. So this will be here an, then this will be an minus 1, this will be the an minus 2, this will be the an minus 3, this will be a of k, and this will be a1, and finally here a of 0. So as we stated, the first line is taken from the characteristic equation. By collecting the coefficient. Now the second line is reversed of the first line. Now we will continue in the jury table until we are reaching 2n minus 3. So here we need to fill the third line, and let's assume the coefficient of the third line is b of 0, b of 1, b of 2, b of 3. Let's assume here we have b of n minus k until I'm reaching bn minus 1. Now the fourth line is identical to the third line reversed in order, which means that here will be bn minus 1, bn minus 2, bn minus 3, bn minus 4, bk minus 1, until we are reaching here b of 0. Now how to calculate b of 0? Now b of 0 will equal a0 multiplied by a0 minus an multiplied by an. So what about if I need to calculate b of 1? Now the first two elements here are fixed, so it will be a0 multiplied by a1 minus an multiplied by an minus 1. So I'm shifting 1 in the direction of reducing the n. What about b2? b2 the same. a0, it will be a0 multiplied by a2 minus an multiplied by an minus 2. So simply here, if I need to write a general form for b of k, it will be the determinant of a0 an minus k a of k. So if I need to find b2, it will be the determinant of a0 an here it will be an minus 2, and here it will be a of 2, and this will be a0, a2 minus an minus 2. The same thing if I need to calculate b1, it will be a0, an, those are fixed, whatever I need to calculate the b's. Then this will be an minus 1, and this will be the a1. So this will be the a0, a1 minus an multiplied by an minus 1. So that's why I'm telling you, if I need to calculate the third line, I need to rely upon the two lines above the third. Then those two elements are fixed all the time. And now if I need to calculate the first element here in the third line, I will rely on the last two elements. So it will be a0 minus an. Now if I need to calculate b1, those are fixed, so I will take those. Then I will go one step, so I will take those two elements. So simply now I can write b1 to be, automatically if I need to calculate, it will be a0, a1 minus an minus multiplied by an minus 1. Now if I need b2, those are fixed. Now I need to take the element which is the an minus 2 and the a2, and so on. Now after finishing filling the elements in the third line, the fourth line is the same as the third line, reverse in order, and this will continue. Let's assume the fifth line here is C0, C1, C2, C3. Here I would have Cn minus k, and so on. Now if I need to calculate the elements in the fifth line, I will rely upon the two lines above it, which is the third and the fourth. So if I need to calculate C0, those all the time are fixed. So C0 will equal B0 multiplied by B0 minus Bn multiplied by Bn minus 1 multiplied by Bn minus 1. So this will equal to B0 minus Bn minus 1 multiplied by Bn minus 1. Now if I need to calculate C1, those are fixed. I need to go one step in this direction. So this will be B0, B1 minus Bn minus 1 multiplied by Bn minus 2, and so on. If we need to write it in general form, now C of k will equal B0, Bn minus 1, Bn minus 1 minus k, B of k. Now the line number 6 elements is the same as the line number 5 reversed in order. So this will be Cn minus 2, Cn minus 3, Cn minus 4, Cn minus 5, Cn minus 2, and so on. And this will continue until we are reaching, for example, here 2n minus 5 line, 2n minus 4 line. I will stop when reaching 2n minus 3 line. Let's assume this one is L0, L1, L2, L3. So this will be the L3, the reversed. This will be the L2, this will be the L1, the L0. Finally, here the last line, let's assume it's M0, M1, and M2, and we will stop at 2n minus 3. So the jury table will stop at 2n, the line 2n minus 3. And simply here we can add a note that only we need to calculate the element of the odd numbered lines. So only find the elements of the odd numbered lines and the even one are reversed in order. So after finishing the Joule table, we are on a stage to write the necessary and sufficient condition for the characteristic equation to have no roots outside the unit circle. So the necessary and sufficient condition for the characteristic equation, and here we call it Q of Z, to have no roots outside or on the unit circle with, here I will state the condition for an greater than 0, and we state that if an less than 0 I will multiply by minus. So the first condition, Q of 1 must be greater than 0. The second condition, minus 1 to the power n, where the n is the order system, Q of minus 1 must be greater than 0. The third condition, an must be greater than the absolute value of a of 0. Why here I'm not writing absolute value? Because I'm assuming that an is greater than 0. Now those three conditions has no relation with the Joule table. Simply those can be calculated directly from the characteristic equation. So if any of those conditions is violated, I don't need to go and build the Joule table if only I need to state the stability of the system. So first check them, and you can stop if any conditions are not satisfied. This will give you indication that the system is unstable. Now, if the first three conditions are satisfied, we need to build the Joule table. Then we'll have n plus 1 condition. So this will be the 4 condition. Let's say the absolute value of b of 0 must be greater than the absolute value of bn minus 1, and the absolute value of c0 must be greater than the absolute value of or cn minus 2, until we are reaching the last let's say the absolute value of m of 0 is greater than the absolute value of m of 2. So the number of the conditions for the stability is n plus 1. So if we return back to the Joule table, so after the three conditions, we need to check if this element p of 0 is greater than this element. Then we go to the fifth line. Then we check if c0 is greater than the last element here, and so on. So let's take example here, and I will start with the following example. Let's assume the characteristic equation is given as z to the power 4 minus 1.2 z to the power 3 plus 0.07 z square plus 0.3 z minus 0.08 equal to 0. So simply here, this is a fourth order system. If I need to find the exact location, it will be difficult. So let's start with the condition of the stability, and the first condition is the coefficient of the z to the power n, which is here 1, is greater than the absolute value of the condition of the power 0, which is here minus 0.08, and this is correct. Now let's check the second condition, which is a q of 1, which will equal, now this will be 1 minus 1.2 plus 0.07, I'm substituting 1 instead of z, plus 0.3 minus 0.08. Now this, if we do the math, will equal 0.09, which is greater than 0. So the second condition is also satisfied. I need to check the third condition. The third condition is minus 1 to the power n, and n here is equal to 4. So minus 1 to the power 4, q of minus 1. Now this will equal, so minus 1, the third condition. So we need to check the third condition, minus 1 to the power 4, q to the minus 1. Minus 1 to the power 4 is 1, q of minus 1 here is 1, plus 1.2, plus 0.07, minus 0.3, minus 0.08, which will equal, if we do the math, this will equal 1.89. This is greater than 0, so the third condition is also satisfied. So we need now to build the Joule table. So here I will say z to the power 0, z to the power 1, z to the power 2, z to the power 3, until I'm reaching z to the power 4. Now the first line is taken directly from the characteristic equation by collecting the coefficient. So the coefficient of z to the power 0 is minus 0.08. The coefficient of z to the power 1 is 0.3. The coefficient of z to the power 2 is 0.07. The coefficient of z to the power 3 is minus 1.2, and finally the coefficient here for z to the power 4 is 1. Now the second line is identical to the first line, reverse in order, so this will be the 1, this will be minus 1.2, this will be 0.07, this will be 0.3, and this will be minus 0.08. Now let's calculate the third line element. If I need to calculate this element here, now those are the pivot. All the time I need to rely upon them. Then this is the B0, so I will take the last two elements here. So this one will equal 2. So let's calculate it here. So B of 0 will be minus 0.081, 1 minus 0.08. Now if we do the math, this will equal to minus 0.9936. Now if I need to calculate this element here, those are the pivot are fixed. I need to take the element here. So B1 will equal the determinant of minus 0.081 minus 1.2, 0.3. If we do the math, this will equal 1.176. If I need to calculate the element here, this pivot is fixed, so I need to take those two elements. So here we have the B3, which will equal minus 0.081, 0.07, 0.07. If we do the math, this one multiplied by this one minus this one multiplied by this one, we are reaching the 0.0756. Now if I need to take this element, then I will multiply minus 0.08 by minus 1.2, then minus 0.3. If we do the math, this will equal minus 0.204. Now the line number 4 element is identical to line number 3, reverse in order, so this will be minus 0.204. This will be 0.0756. This will be 1.176, and finally here I'm having minus 0.9936. Now the number of the conditions we need to have is n plus 1, and the number of the Joule array is the 2n minus 3, so 2n minus 3. So here we have 2 multiplied by 4 minus 3 is 8 minus 3 is 5. So we need the last element, which is the fifth line. Now the same thing with fifth line. If I need to calculate, I will rely upon the two lines above it. So if I need this one, this will be minus 0.936 multiplied by minus 0.936 minus 0.204 multiplied by minus 0.204. So if we do the math, this will be 0.946. Now if I need this one will equal, I will take those two, then I will take those two and find the determinant. So this one multiplied by this one minus this one multiplied by this one. If I do the math, this will be minus 1.184. If I need this one, then I will take those two elements and I will multiply this one by this one minus this one by this one. If I do so, 0.315 I will get. Now we need to check the odd lines after the two lines, so I need to check the third line and the fifth line such that the absolute value of the coefficient of the first element must be greater than the absolute value of the last element, and this is correct. So here we have the absolute value of minus 0.9936 is greater than the absolute value of 0.204. So this is also checked. And the last condition we need is the absolute value of 0.946 is greater than the absolute value of 0.315. So the system is stable. So all the conditions are satisfied, so the system is stable. Let's take another example. Let's assume that the characteristic equation is given as z to the power 3 minus 1.3 z square minus 0.08 z plus 0.24 equal to 0, and we need to check the stability. If I'm writing it in general form, and this is not required and necessary, but simply if you need to do so, this would be a3z to the power 3 plus a2z to the power 2 plus a1z plus a of 0 is equal to 0. Now let's check the condition, the first condition, and all the time you should be sure that a to the power n is greater than 0, and here 1 is greater than 0. Otherwise, I should multiply by minus 1 to guarantee that the coefficient of the highest power of z must be positive. So let's start with a3 must be greater than the absolute value of a of 0, and here 1 is greater than 0.24, so the first condition is checked. Now the second condition, q of 1 must be greater than 0, so 1 minus 1.3 minus 0.08 plus 0.24. Now if we do the math, this will equal minus 0.14. This is less than 0, so here we have violation in the condition, so the system is unstable. I don't need to proceed. If only the stability is my concern, this means that the system is unstable. Let's take another example. And let's recall our previous example, except that k here is unspecified now. And here we have the zero order hold. Here we have the GP of S, which is 1 over S plus 1. And this is a unity negative feedback. This is the R. Let's assume this is the Y. And here let's assume T is equal 1 second for simplicity. Now we need to design K such that the closed loop system is stable. So if we call those are G of S, we need to find the closed loop path transfer function, which is R over. So we need to find the closed loop path transfer function. So Y over R will equal K G of Z over 1 plus G of Z. So from our previous example, G of Z is equal to the Z transform of 1 minus exponential of minus S. Here T is equal to 1 over S, 1 over S plus 1, which will equal 1 minus z minus 1, the z transform for 1 over s square s plus 1. Now here g of z will equal to 0.368 z plus 0.264 over z minus 1 multiplied by z minus 0.365. No, 68, sorry. So the characteristic equation is 1 plus k g of z equal to 0. So we can write the characteristic equation as 1 plus k g of z is 0.368 z plus 0.264 over z minus 1 multiplied by z minus 0.368. So our characteristic equation now can be written as, simplifying, collecting the term, z square plus 0.368k minus 1.368z plus 0.368 plus 0.264k. Now, the condition for stability, I will start. The first one is the coefficient of the z to the power n must be greater than the absolute value of the coefficient of z to the power 0. So 1 must be greater than the absolute value of 0.368 plus 0.264k. So from here we can say that k must be greater than minus 5.18, less than 2.39. Now the second condition is q of 1 must be greater than 0. So if we evaluate q of 1, this would be 1 plus 0.368k minus 1.368. Let me fix this one. Z here is multiplied by all. Yeah, sorry for that. And we have here plus 0.368 plus 0.264k. So from this condition, this must be greater than 0. So from here, this implies that k must be greater than 0. Now the third condition, which is minus 1 to the power n, q of minus 1 must be greater than 0. So minus 1 to the power 2, q of 1, if we evaluate, this will equal 1 minus 0.368k minus 1.368 plus 0.368 plus 0.264k must be greater than 0. Now, from this condition, we can reach to 2.736 minus 0.104k greater than 0, which implies that k must be less than 26.38. Now, all the conditions must be satisfied. Combining all the conditions, we find the range of k so the system is stable. K must be greater than 0 because it must be positive, and here k is less than this one, and from here we have k must be less than 2.3, so k must be less than 2.39.